Okay, so now I'll share my screen also. So is the presentation visible?
Yes, sir.
Okay, okay. So let's go. Good evening, everyone. Thank you for joining this week once again. This week we are going to see on the theory of XRT, but we'll focus more on gate problems today. So, anyone remembers the summary from last class? We'll finish this as quick as possible.
In general, we practiced on the basis of uh, X-ray diffraction. Actually, I even forget that. Just let me check for you.
Ah, sure, Ajit, no problem. Yeah. Or if not, I'll start explaining.
Yeah, we practiced about X-ray radiographic inspection.
Yes.
What are the X-rays? Uh, and X-ray diffraction, XRD analysis of polycrystal material,
Yeah,
X-ray diffraction indexing of cubic crystals. I mean Bragg's equation.
exactly. So we were focusing on first the what are X-rays, then about the characteristic uh,
Application of X-ray
X-ray.
diffraction,
Yeah, and then how X-rays are.
pattern of a metal with cubic structure.
Exactly. So how X-rays are used to obtain single or polycrystalline structures,
Huh.
and then we finally saw the problem. That is
Huh.
how to determine what crystal structure just from XRD peaks.
Huh.
So we saw this. So this is our primary discussion for last week. Okay. So that's what is mentioned here. We also saw about what is constructive and what is destructive interference. To sum this up,
Non-destructive testing.
uh-huh.
Non-destructive testing and
NDT also, yes, yes. We also saw non-destructive testing, like how X-rays are used there. Uh, so, in to sum this short, right? Constructive and destructive interference. If the phase, okay, this is phase, okay. If the phase difference is greater than zero point 0.5, okay, then there will be destructive interference. That is, say, if we have a wave like this, okay, so this is half, okay, half of the wave, and this is the other half. If the phase difference starts over here, okay, here it's supposed to go down, but here, if it starts like this, and then, sorry, so if it's here, so it's supposed to start from the initial value and then go down. It's supposed to be like that, but if there is a phase difference, it will actually start from a higher value. Sorry, you get the point of phase difference, right? So it will be like instead of here the high value, uh, so okay, there will be a complete difference in the waves, right? So they won't perfectly overlap, rather there will be a shift, right? If this sort of a difference happens between the two X-ray beams striking the material, we will have destructive interference. So this is clear, right? And
Yes, sir.
the phase difference should be greater than zero point 0.5, that is greater than half. So this is constructive versus destructive equation. Then we saw about Bragg's equation, n lambda is equal to 2d sine theta, and then lattice parameter determination using XRD. Then contents of today's classes, we will see about the Scherer's formula. Mostly we will discuss regarding the problems only. If we have time, we will go for phase diagram determination using XRD, and microscene determination also is part of the problem, so you don't have to worry about that. So if we have time, we will go for this, because this is not very useful for gate, but this is very useful when it comes to your higher studies. So we'll see, if we have time we'll go for that, otherwise we will not do it. Okay.
Okay, sir.
Yeah. So first, last time you had asked some questions, so of which there were totally 4 questions that were asked. So one was reverse loading, the other was slip directions, that is cup and cone failure, or whether it is slipping according to the 45-degree angle, like straight. Instead of cupping and cone mechanism, will it be like a flat surface? So these were 2 doubts. So for this the answer is quite tricky, and I'm still searching, and I'm not getting proper answers. But I searched the other 2 questions. One was slip across the grain boundary, and the other is what happens when to the source electrons when it strikes the target. So to address the first question, which is slip across the grain boundaries, what it does is the slips tend to increase at the grain boundary. So if you see over here, we have the grain boundaries. It is free only. Free in the sense, if we look at the grain boundary, right, it will only be 1 or 2 atoms thick. So what we can say is, in other words, it will be in a matter of something within 10 angstrom range, okay, which is very very low. Means that if just one atom slips across, okay, it's not going to cover that great a distance. So overall, the slip across the boundaries or slip at the boundaries won't contribute that much to the slipping as such, the total slip. Okay, the major contributors will always be the uh, slip plane and slip direction, because if you have similar slip planes according across different boundaries, right, then what will happen is the chances of it slipping across will be very very high. Another factor is, the lower the angle, like grain boundary angle, the more chances of slip. So if you would look at here, no, between these 2 grains, the angle of misalignment is very, very high. So what happens is, when we apply stress, what will happen is, these set of atoms will go and they will collide with this set of atoms, and since the sorry, the direction of travel will be like this, whereas for these atoms the direction of travel will be in this direction. So what will happen is, there will be like a collision, and that collision will restrict further slip. Whereas if you look at these two grains, what is happening is, here the atoms are traveling in this direction, whereas here the atoms are traveling in this direction. So the angle is actually very, very minimum, so that when we apply the stress, this set of atoms will somehow manipulate the other atoms to travel in the direction of stress, so that the slip is transferred across the boundaries. But at the boundary, it's actually very limited space. So though there will be very quick transfer of atoms, it won't be enough to cause a significant difference in the slip. So is my point clear across the, according to this one, slip across the grain
Yes, sir.
boundaries? Okay, so
Yes,
this,
sir. Actually,
yeah,
prior you have discussed this topic as well.
yes, yes,
Slip
yes, I
across
have.
drain boundary.
But what wanted to do was, like, I wanted to give some more sources. Another thing is, just I wanted to confirm.
Okay,
So
sir.
this is clear, right?
Yes, sir. Yes.
Okay, okay. So next, the question is, what happens to the source electrons after they strike a particular target, right? So what did we initially see? We saw that an atom consists of the target atom. A target will consist of mainly copper, okay, copper atoms. So there is the nucleus, and then you have all the electrons surrounding the nucleus, right? So this is the nucleus, that is the electrons, and then here is the source electron, okay, and that comes and that disturbs this particular electron, right? This either knocks it off, or yeah, mostly this knocks it off. It knocks it off, and what happens to this particular electron is, it either stays in this particular orbit after knocking this off, and this electron becomes a free electron in the copper target. Either that happens, or this electron, source electron, comes in, after knocking, this loses energy, and sorry, and uh, it also becomes a free electron along with the other electron. So you get right what happens. Mostly it gets bound to the nucleus, or if there is too much of excess energy, it just gets knocked out and it becomes another free electron roaming in the target material. So this is kind of clear, right?
Yes.
So actually the thing is, copper is a metal. We think we already discussed in the first class, and it will have a sea of electron, meaning lots of free electrons, right? And they will just be traveling throughout the target, right? and this electrons that are going and impinging, right, they will stay there itself. They will get absorbed, means they will stay there and they will keep continuing to move, and either that or they strike this particular target, and then that electron which comes out will be moving, whereas this will be rotating around the nucleus of the atom. So you get this, right? Is it clear? Okay. Um, uh, Maybe another time I will try to explain it even further, because this is a little complicated explanation because it involves more of physics. So, shall I move on, or is there any doubts?
Yes, sir.
Yes, Avjit?
No doubt, sir.
No, no, okay, okay, yeah. So, next, to determine the grain or crystalline size using XRD, we use the Shirer's formula. I think you would have already come across this Shirer's formula. So, just I have a doubt. Do you want me to discuss regarding the derivation, or can we directly go for the problems?
We can go for the direct problem.
Yeah, yeah, because derivation is not that useful actually. So, we'll go for the problems
Not
itself.
useful, but
Yes,
yes, sir,
Avjit?
useful, but at that moment,
Yeah,
there
for
is
gate, it's
a
not
bit
useful.
time problem.
Yeah, I mean, it's generally useful, but I'm saying for gate preparation, and time is also running out. So, better not to discuss the derivation. So, please note this particular formula, okay? So, this is the Scherrer's formula. B is equal to k lambda by L cos theta. So, k is the constant. So, that is, it will vary from 0.9 to 1.2. So, L is the FWHM, that is full width at half maximum. Usually they give L in terms of degrees. We have to convert it to radians, or sometimes if we are lucky they will give in radians itself. So, just a minute. Yeah, sometimes they will give in radians itself. Okay, so we'll discuss problems on that.
Okay.
This is another formula. So, this is for determining the microstream. And then again, this is XRD result. So, a perfect XRD result will be like a straight line that you see over here, right? But the thing is, in practicality, it won't be a perfect line like this. Rather, it will have some sort of deformation. That is peak broadening, we can say. So, one can be due to instrumentation error. Then another thing is a combination of instrumentation error and crystallite size. That is, if the size becomes larger, okay, more coarse, then there will be peak broadening. And finally, if it's very broad in comparison to its previous result, then all of the above that we discussed so far, that is instrumental error plus crystallite size plus we will have lattice strain. So, this is clear, right? And as we mentioned, like for for single crystal, the peaks will be very, very sharp, whereas for polycrystalline materials, there will be broadening of the peak due to, there is actually a phenomena where, when the X-rays reflect, okay, if there are too many deviations, there will be a cutoff. So, that angular cutoff will be more in polycrystalline materials. So that will cause it to, that will cause the peak to broaden. So I know it's a little confusing, but just this is just for your information. So again, I mean, this is not a problem, but this is a question that was asked in GATE. So line broadening, we just discussed this. Line broadening in X-ray, sorry, not line, this is actually peak. They made a mistake last time. So peak broadening X-ray diffraction pattern occurs on account of what of these things?
Sir, coarse crystalline size.
Exactly. The answer is coarse crystalline size. Because we just saw, no, last time. That is,
Huh.
as the size of the crystal, I mean, becomes larger, okay, and more coarse, what will happen is the angle, what do you call that?
Bragg's
The
law or X-ray diffraction.
yeah,
On the
the
layer by layer, yeah.
more the number of layers,
Hmm.
more the chances of deviation, chances of what do you call that? Deviation in the subsequent angles, right? Sorry, in the subsequent planes, the deviation of beam in the subsequent place. So that will cause the broadening of the peak. So you got it right?
Yes.
Yeah. So the answer is coarse crystallite size. Okay. Now we are going to discuss the main problems that are usually asked. So first we have, if the space between two consecutive 110 planes in a BCC material is 0.2203 nanometer, the lattice parameter and the radius of the atom will be. Can anyone tell me like how to approach this particular problem? Can you tell me what are the given data for this problem?
Yes, sir.
Yeah.
So could we apply by using the that like on the result, like we use that for calculating resultant vector in that way?
Okay. So to approach this particular problem, what we do is, um,
Like
yeah,
HKL, like for crystal theory.
yeah. We use the HKL because the HKL values are given here. Then we have
Hmm.
to find the lattice parameter, right? So
Mhm.
first we'll write the data. The data will be the spacing between the two planes is so much. That is D. Okay, also known as interplanar distance. So this is given, right? HKL values are given and crystal structure is also given, right? We should find the lattice parameter and the atom's radius. So for this, the solution is, do you know this formula? D is equal to A by,
A by root of h square plus k square plus l square for
exactly,
cubic crystal.
exactly. So this is the, for finding
Miller
the
indices.
interplanar distance of the cubic crystal. So
Mhm.
any cubic, this can be BCC or FCC or SC. Okay, for any cubic crystal, this is the formula, general formula. So we know the D value, that is 0.203 nanometers, and we also know the HKL value, right?
Hmm.
Into root of 1 square plus 1 square plus 0, and we get the value of A, right? So the value of A would be around, uh, did anyone calculate the answer yet?
Doing
Okay, yeah, please let me know.
root 2 into 0.203 root 2.
I'm sorry. Root 2 into?
0. Point
Yeah, the answer, the A value is?
into root 2. 0.2870.
Exactly. 0.2870. What unit will come?
Armstrong.
No. Reason why it's not Armstrong is because the D value here is given in terms of nanometers. So the answer here will be nanometer only. Okay?
Okay, okay, okay. Yeah.
0.2870 nanometers. Okay, very good. Now how to find the radius of the atom? Any clue?
Sir, A equal to 2 root 2 R.
Uh, yeah. Oh, no, no. Actually, for BCC, it is supposed to be root 3a is equal to 4r. I believe
Ha ha ha.
2 root
Pardon
2r
me,
is
sir.
FCC, I guess. Yeah.
Ha ha. FCC. Actually, I'm missing.
Yeah. So, for BCC, we know that root 3a is equal to 4r from our previous calculation, right? So, from this, we find the r value. R is equal to root 3a by 4. Can you tell me what the r value is?
Yes, sir. Doing so.
Yeah, yeah.
Two roots, two, three, 0.1242.
0. Point?
1242.
Exactly. 1
7.
to 4 to nanometers. This is enough. Yeah. Up to 4 decimal place is enough. So, very good. This is the answer. So, now we have found the lattice parameter and the radius of the atom. So, this was a GATE 2009 question. This is a 2 mark actually.
Okay, that's a bit easy.
Yeah.
Sometimes there's a probability of making mistake on the like for the radius part, calculating radius part, because
Exactly.
for
BCC and
FCC.
FCC is a problem. For FCC, it's actually root 2a is equal to 4r. Because if we calculate the phase, no? So, this is FCC, right? From one side, okay? We are taking one side. So, this will be A, this will be another A, and for this side, according to Pythagoras theorem, it will be root 2a. Am I correct?
Yes, sir.
So, we will have root 2a is equal to, this is 1r, then these are two radiuses. So, 2 plus 3r, and then finally one more r here, which is 4r. So, root 2a is equal to 4r for FCC, but BCC we can't do this, right? BCC it will be like here, then there will be one in the center, okay? So, in that case what we should do is say going to the top view, we have to find the diagonal, okay? I'll draw this in dotted lines. You have to find the diagonal. Here A means in this place it will be root 2a, and then okay, this is a little difficult to draw. And then this is the body centered cubic. So this is the body center atom. So we already know that this is a root 2a, and then there will be another a over here. Finally, in the hypotenuse, we will get a root 3a. So this is clear, right?
Yes, sir. Yes.
Yeah. So we should never forget, for BCC, it's root 3a is equal to 4r, and for FCC, root 2a is equal to 4r. Okay, so we'll see some more problems. Next is Ajit, I'm getting some feedback. Okay, no problem. Coming back. So nickel has a FCC structure and its lattice parameter is 0.353 nanometers. The weight of 1 mole of nickel is 0.05871 kilogram. Then the nearest nickel-nickel neighboring distance is, this is in nanometers. Okay. And the theoretical density is closer to what value? So does anybody know how to solve this?
Trying, sir.
Okay. So since time is running out, I think I'll directly go for solving the problem. Okay. So the data that is given over here is, meanwhile Avijit, you can solve and you can tell me the answer when I'm asking. Okay. So here, what is happening is, it's spacing. Sorry, this is from the previous problem. Sorry, I'm so sorry. There is a mistake. I'm so sorry. What happens is here, FCC crystal structure is given. Then lattice parameter. Lattice parameter means we will consider as A.
A.
A is equal to 0.353 nanometer. This is given, right? And then the weight is given. That is atomic weight. It is 0.05871 kg per mole, right? This is given, right? And what should we find? The distance of the neighboring atom. We can call it D, okay? And then the theoretical density. These are the two things we have to find, okay? We also know that if there are two atoms, right? Theoretically speaking, its radius is actually equal to the diameter, right? I mean, theoretically. So, based on this particular phenomena, we are going to solve the problem. Okay. So, here what is given? FCC is given. So, we also know that for FCC, okay, root 2a is equal to 4r. We just discussed in the previous problem, right? This is the common method of finding the radius, because what we have to do is we have to find the value of the diameter, and that diameter will correspond to the nearest neighboring distance. Okay. So what shall we do? We know the value of a already, right?
A.
Yeah, that is already given. So r is equal to 4, sorry, root 2 a by 4. So what is the answer, Avinash? Did you get?
0.1248.
Exactly. 0.1248 nanometers, right? This is in terms of radius. Now what do we want? We want the diameter. So diameter is
2 into
2 into 0.1248, which is equal to 0.2496 or around about 0.25 nanometer. Okay. So now we have found the nearest neighboring distance, right? Now we find the theoretical density. Does anybody know the formula for theoretical density? We'll do it in the next page.
Yes, sir.
Yeah.
D equal to small n into m by a cube na.
Okay. Do you know what this N and M stand for?
Yes. Small n represents unit cell in FCC.
Yes, number
M
of
means,
unit cells.
M means molar mass,
Perfect.
and
Molar
A is
mass.
the age length, and capital N is Avogadro's number.
Exactly. This is the what we can say is the whole A cubed is volume. of the unit cell.
Hmm. Hmm.
Okay, and this is the Avogadro number.
Sir, isn't that A is the edge length, sir?
Exactly. I mean, A is age, this edge length. That's true. But we can take the whole terminology, right? Because what
Okay.
will happen is this will vary in terms of HCP. HCP it
Hmm.
becomes more complex. So we won't get a direct A cubed. So for that we have to solve and we should write in terms of the volume. Remember
Hmm.
last time we wrote it was a little complex. I forgot the formula that we wrote. Remember?
Hmm. Hmm.
So
Huh, huh.
I think it's there in the previous slides. You can check it out. So what are the number of unit cells in FCC? 4.
4.
Then
Yes.
molar mass. What did we see as molar mass? 0.05871. Am I right? Sorry. 5871. We have to be careful of the units. Kg per, sorry, mole. Kg per mole. Okay. Usually, if nothing is given, right, molar mass will be in terms of grams per mole or AMU. Usually this will be the unit, but here it is given in kg per mole. So we have to be careful, right? Then what else? Um, we have lattice parameter. What is the lattice parameter? 0.353, right?
Yes.
0.353 whole cubed into what else? Avogadro number. What is Avogadro number? 6.026.
6.023.
Sorry, 023 to 10 power 23.
23.
Right? So can
Yes, sir.
someone tell me the answer for this?
Yes, sir. Doing, sir.
Yeah, sure. So the answer will be something around uh, 8,900 kg per meter cube. Always think, look at the unit that is asked in the question. If it's in kg per meter cube, the answer should be in kg per meter cube. In case of gram per meter cubed, then we should convert this to gram per mole.
It's coming, sir. 8.56 into 10 to the power minus 4.
8.56 into
Into
10
10 to the power
power
minus 4.
minus 4.
Hmm.
Oh, just a sec. You added, okay. Sorry. Here I forgot to mention about this thing. This is in nanometers, right?
Okay.
0.353 nanometers. So did you did you write it like this, Abhijit, or?
No, I missed that nanometer parts.
Okay. So I think that would make a difference, I guess. So if you try it, the answer, I mean, as far as I know, the answer I got was 8861.8, if I'm correct. So this was the answer that I got.
But I am getting, sir, 8569 even after doing that.
Oh, 8569. Yeah, that's all right. I mean, somewhere close to the actual answer. Wait. This is 10 power 23.
Hmm.
What else is there?
Minus 9, 10 to the power 14.
Uh-huh.
And that cube,
Uh,
10 to the
uh,
power 17.
okay, wait. 9 3, sir. Actually, you'll get 10 power 27, right?
Hmm.
So 0.353 into 10 power minus 27 into 6.023 into 10 power 23. So we'll get some answer into 10 power minus 4, right?
Hmm.
And that goes on top, it becomes 10 power 4.
Hmm.
So, okay, I mean, this is fine if it's anywhere, I think around 8,600 to 8,900.
Okay.
So, If the answer is somewhere close, it's sufficient. But we'll see, because I got this particular answer 8861.8.
Okay, sir.
Okay, so moving on. Now we'll come to this problem. The first peak in powder XRD of FCC metal appears at a Bragg angle of 19.2 degrees. The wavelength of copper K alpha radiation used is 0.154 nanometers. The lattice parameter of the metal is dash. And also calculate the crystallite size of the sample when the full width half maximum is 0.35 degrees. So does anybody know how to approach this? Okay, so I'll explain. So what is given? We have the first peak, okay, and then the Bragg angle is also given. That is the theta value, not the 2 theta value. Okay, until and unless they mention that the value given is 2 theta, you don't consider that as 2 theta. Okay, consider that as theta alone. I'll write here. Don't consider.
Sir, that would applicable that same formula.
Yes.
I think I can do that.
There will be a slight difference in the formula. I mean, slight difference in the sense it is using a different formula actually. If
Sir,
you
for calculating lattice parameter and radius, we should apply the same formula, right, sir?
for calculating lattice parameter,
Hmm.
let's see. We have wavelength, but there is one other formula which can be used. Can you try it? I mean, here what is our usual formulas? D is equal to a by root of h plus k plus l. Okay, so d value, but d value is not given here, right?
Yes, sir. D is not given.
So if d is not given, we can't use the previous formula. But we can use this particular formula. Wait, we can use.
Miller indices. Miller indices.
Yeah. So for that, you may have come across this, right? Lambda square by 4a square is equal to sine square theta by
Hmm.
h square plus k square plus l square.
It's elsewhere.
So this is a formula that we use. Did anyone get the answer? Did Avijit, did you get the answer yet?
Doing, sir, doing.
Okay, okay. Yeah, take it time.
Sin square theta.
So meanwhile, we'll just substitute the values. So what is given? Wavelength is given, right? So 0.154 nanometers, that is given, right? Lattice parameter, is it given? No, we have to find it. 4a square. Then sine square theta value is given, 19.2 degrees, right? And HKL
Sir, here
value, yes,
FWHM means, sir?
full width half maximum. So we saw in the previous case, right? Full width half maximum.
So sometimes they could use this kind of short terms, right, sir?
Yes, yes, that's why it's a very common term. So we should remember this FWHM, full width half maximum, or full width at half maximum. That is for the XRD peak, the width at half of the maximum peak value. Okay, which is somewhere around here, right? So that is this FWHM. Okay. So there is one more trick over here. The HKL values. So did anyone know what the HKL values are?
So, would it be, sir?
There's also a clue. This is the clue.
Uh, so then 110.
No. If it was BCC, then your answer would have been correct. 110, because we saw in the previous class, right? For BCC, H plus K plus L should be equal to even. So the first peak will begin at 110, because 1 plus 1 plus 0 is equal to 2, right?
True.
And that is even, and that is BCC, right? But if it is FCC, then H comma K comma L should be either even or odd. Okay, so the first peak for FCC will be 1 comma 1 comma 1, because all three are odd, right? So your answer will be
That
1.
would be 3.
Yes, so your answer here will be 3. And if we substitute, your A value will be somewhere around 0.4055 nanometers. I'm sorry, I have to rush because there is only 5 more minutes. So I'll just quickly explain the problem and I'll go. So next is to calculate the crystallite size of the sample, right? Does anyone know the formula for calculating the crystallite size? We will call that VC. Okay. Okay. Since time is running out, I'll write it. K lambda by L cos theta. Let us assume if nothing is given, okay? Assume K is equal to 1 if nothing is given, right? In that case, we have 1 into, what is the lambda value? Lambda value is 0.154
1.15.
divided by, what is the L value? L value, actually we are, sorry, L is FWHM. Sorry, I wrote a different terminology, I guess. Yeah, L is a HWHM, and cos theta value is 19.2. Am I right? Yeah.
Cos 19.2.
And here there is a catch. The FWHM is given as 0.35 degrees. So if it is given in degrees, what we should do is convert it to radians. So 0.35 degree into pi by 180 radians, right? In that case, what we have to do is just substitute here. BC is equal to 1 into 0.154 divided by 0.35 into pi by 180 times cos 19.2. Did anyone get the answer meanwhile?
Doing.
Yeah, sure.
আচ্ছা বলতে হচ্ছে 514 0.1554 by
0 point.
doing cos 19.2.
So okay, since time is running out, I'll tell you. So oh god, okay, I'm having low battery. Okay, meanwhile try to finish. So the answer I think will come around 26 nanometers if I'm correct. So maybe you guys can try this out afterwards. This time is running out. We have to go. So we just have another two more problems. Okay. This is a very straightforward problem. Does anyone know the answer to this problem? Or just the approach?
Here has a pieces you have to look into interrupt. That one also first different way.
So maybe I'll do one thing. Yeah.
Should we apply that Bragg's formula for the in that case?
Yes. Perfect. You're right. You have to apply the Bragg's formula for this. But before that, you should do some things. Okay.
Yes, sir.
That is, you should find the d value.
D value.
Okay.
Lambda by d equal to 2 sine theta.
Yes. And there is also another problem. We do not know theta. Because the question is find 2 theta. So this is the final. 2 theta will be your final answer. Okay. So can you guys try this as a homework and come? Maybe we'll discuss in the next
Yes,
class.
sir, that we could calculate also theta like theta when we apply theta then we could get sine inverse value from that sine inverse value we could get that theta.
Yeah. That's it. Exactly. But the final thing should be 2 times of your theta. Because here it says 2 theta. It was mentioned specifically in the question. Find the first diffraction position 2 theta for copper K alpha radiation. So can you guys try this as homework? Maybe
Yes,
next
sir.
class we can discuss. Okay.
Yes,
It's
can't do that.
yeah, it's quite easy only. Maybe this problem we can give it a try. Calculate the density of copper. This also I'll give you as homework. These two problems. What do you say? Because
Yes, definitely. That first one I got it.
oh, you got it. Okay, good. We'll discuss. Tell me. What is the answer?
First one would be like 51 degree.
51. The theta.
Mhm. I
Actually,
mean,
the
actually I rushed, therefore might be wrong, but I got that how to use that formula.
okay. Okay, maybe I'll do one thing. I'll tell you how I solved it. Okay. So for me, what I did was
Sir, sir,
initial.
don't,
Yeah.
sir, don't tell me. Don't tell me. I got it. How to do it?
Okay. So you got it right. No, but for
I think.
others, maybe for others, I can give a explanation and maybe we can end today's class. What do you say?
Yeah. Yes.
Okay. For others, in case you haven't solved it, okay. First, we see that we have a BCC structure over here, right? And then we know for BCC, the formula is root 3 is equal to 4R,
4 hours.
right? And let's take this in terms of diameter, okay? So root 3a is equal to 2d, right? Oh no, okay.